Am I audible? Am I audible?
Yes, sir.
Okay. So, start of this particular subject, theory and analysis of composite material, as per the MTech Mechanical Design Engineering, with effect from the syllabus which is applicable presently for this subject for MTech Mechanical Design. In the curriculum of Punyashloka Ahilya Solapur University, we up till now completed the first chapter, Introduction to Composite Material. Second chapter, Macro Mechanical Behavior of Lamina. Third chapter, Micro Mechanical Behavior of Lamina. From the section first, all these three chapters are over. Starting from second section, Macro Mechanical Behavior of Laminate. This part we have started, but before that we have completed the manufacturing layup and curing. So this total chapter is over, and presently we are working on this macro mechanical behavior of the laminate. Is it okay? So here we should know the introduction code, introduction, lamination code, Kirchhoff's hypothesis, classical lamination theory, and ABD matrix, even matrices. Okay, so this particular part we have to study further with this, and as a part of this particular syllabus which is present for our curriculum, macro mechanical behavior of laminate, we are taking reference of macro mechanical analysis of this laminate. Starting with this particular part, during last lecture we have completed the part of this laminate code. So we have seen for this laminate code that in case of any laminate, number of such a laminas are present. So many such a laminas which are put together one another second like this, the laminates are manufactured. So this is like one heap which is kept one pile, another separate piles like this. Each and every layer is of different what we can say that angle lamina, and that's why each and every lamina has its own stacking sequence. Is it okay? So like this stacking is there and that sequence is followed later on. Is it okay? So this laminate is made from different laminas. So during last lecture we have seen that, suppose this particular figure, in that figure this portion which is at the bottom, this is one lamina, this is another second lamina, this is third lamina. So one, two, three laminas are there. All these three laminas are put together to form one laminate. Is it okay? So if we consider this as a first lamina, second lamina, third lamina, then each and every lamina has its own particular angle, and this angle will describe this sequence. Is it okay? And together that total sequence is kept here. Is it okay? So this is the schematic of laminate. Now here we have seen this particular laminate code, and this particular code put together will be considered as the sequence. Is it okay? So here 0, minus 45, 90, 60 and 30. That indicates that 1, 2, 3, 4, 5. These 5 layers presently are present. Bottom layer having 30° to the x-axis, because angle is measured to the reference x-axis. To reference x-axis, the fibers are at an angle 30°. Second, the fibers are at an angle 60°. Third, fibers are inclined at an angle 90°. Fourth, fibers are inclined at an angle minus 45°. And fifth, this is at 0°, that is in the direction of reference x-axis. So This is one way that if there is no any kind of what we can say as the different sequence, directly we will use this 0 minus 45 oblique 90 oblique 60 oblique 30 as shown here. Is it okay? Like this we should refer here. Then that consists of 5 plies and each has different angle with reference x-axis. Is it okay? Now let us check another example. In this second example, we are considering 0, minus 45, 90, 90, 60, and once again 0. So in order to represent this kind of stacking sequence, now how we can represent 0 slash minus 45 slash 90. So by putting these two to 90 together, we are referring this as 90 to the base 2. Is it okay? So how this is represented? See here, 0 oblique slash minus 45, 90 to the base 2 slash 60 slash 0. Is it okay? Like this is represented, and that denotes the laminate above, which consists of 6 plies. Because two 90-degree plies are adjacent to each other, 90 suffix 2 denotes that this the two adjacent layers which are having same that we can say it as the subscript 2, that is same angle 90 degree, that is present here. Is it okay? Similarly, for this next case here, 0 oblique minus 45 oblique 60, here you can see that 0 minus 45 60, again 60 minus 45 0. So 0 minus 45 60, and symmetric of that which is present at the bottom layer. In the top layer 0 minus 45 60, and to the bottom layer 60 minus 45 0. That means this particular 0 minus 45 60 sequence, that is repeated from the bottom end also. From top end 0 minus 45 60, and from bottom end 0 minus 45 60, and same sequence is repeated from top end to the bottom end. So here we can consider this as the symmetric. Is it okay? So yes is used, yes, this designation is used to the bottom as a suffix 0 oblique minus 45 oblique 60, and to the base yes, that denotes the laminate above consisting of 6 plies. Is it okay? The plies above the midplane are of the same orientation, material, and thickness as the plies below the midplane, so that it is symmetric laminate. Is it okay? Like this, 0 minus 45 60 minus 45 0. So 0 oblique minus 45 oblique 60, and symmetric of that denotes this laminate which consists of 5 plies. Is it okay? So here we can consider this bar is used at the top. Bar is used that denotes this 60, that it's a mid level, and 0 and minus 45 which are used from the top as well as from the bottom side, that denotes this laminate which consists of 5 plies, out of which 60 is that it's a mid level. Is it okay? The number of plies is odd, and symmetry exists at the mid surface. Is it okay? So here bar notation is used at the top 60 bar. This kind of designation has been used. 0 and minus 45 at the top, and 0 and minus 45 at the bottom also. So one more example here we can see 0 45 minus 45 minus 45 45 0. So from the top side 0 45 minus 45, from the bottom side 0 45 minus 45. Is it okay? Like this kind of structure from the top side and from the bottom side that is present here, that indicates that there is a symmetry, and as same angle but in negative sign is given here, plus 45 and minus 45 is present here from the top side. From the bottom side also same kind of sequence is followed, plus 45 minus 45. That's why this kind of stacking sequence is represented in square bracket as square 0 slash plus 45 minus 45 and to the base yes, that indicates this is the symmetric. Is it okay? But additional to that, one more word here it is used in order to indicate which is the layer of matrix and which is the layer of reinforcement. Is it okay? So here if we see the way of representation here, that indicates that in square bracket 0 degree graphite oblique plus and minus 45 boron is used, and this is the symmetric here. Is it okay? So 0, this is graphite, boron. So this plus 45 is boron, minus 45 is boron, and again once again minus 45 plus 45 are boron, and then once again graphite is present here. So 0 graphite, that means there is no any kind of reinforcement angle for this. This is towards the reference x, this is in the direction of reference x axis. So 0 gr, that indicates the angle of that indicates that 0 to the upper end gr, that represents the graphite which is present here, and for remaining, because this is hybrid type of composite, so that's why here more than one reinforcements are used. Is it okay? Epoxy is the matrix material, but graphite and boron that are used as a reinforcement material. But at which location graphite is used and at which location boron is used, so that is represented here. The top layer is made from graphite epoxy, middle layers are made from boron epoxy, and bottom layer that is again manufactured from graphite epoxy here. Is it okay? So 0, so here prefix and suffix like this, here gr is used. So this gr represents the graphite, means top layer of this total construction, top and bottom layers both are manufactured with the help of graphite, and remaining layers that are manufactured with the help of boron as a reinforcement material. But for total construction, epoxy is considered to be a matrix only. So matrix is same, but reinforcements are graphite and boron here. Is it okay? So this designation for this particular with laminate code is 0 gr slash plus minus 45 B, and this is symmetry here. Is it okay? So like this, this laminate codes we should understand here. Is it okay? Then with usual notation, stress is force upon area, strain is normally we already use the strain as P upon A. This is our regular assumptions. Is it okay? So same kind of assumptions now for stress strain relations and these laminates we are going to use, because further we have to move for some of the fundamental equations. Before that, let us consider that P is the amount of force applied for this particular element which is considered here. Suppose we are considering the beam as element, then for this beam, suppose P, this is the tensile force applied here, this is the bending force applied here. Here we can see that this both sides, this curvature portion shows that this is the bending here, and this particular case is the combined loading, that is tensile as well as bending, both are applied here. So in first case axial load, in second case bending moment, and third case combined axial and bending moment are applied here. Is it okay? So by this way here, if we go for this analysis of bending analysis of that, then here we'll come to know that strain is where rho is the radius of curvature. Here we are already familiar with this equation or flexural formula, that m upon I is equal to sigma upon y is equal to E upon R. Is it okay? So same thing is used here. The radius of curvature we know, then the stress sigma for that equation m upon I is equal to sigma upon y. So m upon I, which is used here, and sigma upon y. So for that purpose, this z terminology, so z is the distance from centroidal axis. Earlier we were using the notation y whenever you were in the second year. M upon I is equal to sigma upon y. That was the terminology used, but y is here noted with this z, and that indicates the distance from the centroidal axis. Is it okay? So this moment of inertia always integration z square dA here. So for combined loading condition, what was used in this figure 3, if we try to identify the strain acting, then that is addition of both the cases. Here this mz upon E, this mz upon I is the stress, and if suppose I divide here with Young's modulus, then mz upon EI, that may be the strain present here. Is it okay? So this strain present mz upon EI, and the second strain P upon AE. Addition of these both the strains, that will be the strain along x-axis. Is it okay? The strain along x-axis, that is the addition of these two strains, out of which first is tensile strain and second is due to the bending only. Is it okay? So addition of these two will give the strain along x-axis, because this is combined tensile and bending phase. Then strain along x-axis, that is with reference to its central strain axis, that is given here as epsilon 0 is equal to z upon 1 upon rho, because in this case already we have one derivation available with us, that this particular strain along x-axis is given as for first case, that is z upon p. This is the distance from central axis, and this is the rho, that is the radius of curvature here. Is it okay? With that basis, if we use this z upon rho here, so this z upon rho, that is already will be replaced for this particular portion here. Is it okay? So this particular bracket, this portion, the which is after this plus sign, that can be changed with z upon rho here, because this is the radius of z, is the distance from central, rho is the radius of curvature here. Is it okay? And this epsilon 0 is the strain at z is equal to 0. That means whenever the radius of curvature, whenever the distance from centroidal axis is 0, this strain is given. Is it okay? Because tensile strain is always measured at the neutral axis only. So that's why at its center, at its neutral axis, for the symmetric figure, at its center, this neutral axis will be present, and that's why the strain present due to this tensile load at its neutral axis, that is given as epsilon 0, and second one plus z into 1 upon rho is used here. Is it okay? Then addition of these two will give the strain. So epsilon 0 is the strain at z is equal to 0, that is the centroid line of the beam, and k is the curvature here. Is it okay? 1 upon rho, that is the replaced as equal to k here. So k represents curvature. Is it okay? Here k represents curvature. So 1 upon rho, that is the, this rho is radius of curvature, and k is represents as a curvature, which is the reciprocal of this radius of curvature. Is it okay? So radius of curvature, we know that rho, how it is identified from this figure only. We will come to know that this particular radius of curvature, it will have certain centroidal axis here, and from that it may be have curved, so that will be the rho here. Is it okay? So rho is considered to be radius of curvature here, and then this z upon rho, or this 1 upon rho, may be considered as k, or radius of curvature here. So z into k, epsilon 0 plus z into k here. Is it okay? So epsilon 0 is the strain at z is equal to 0, and that is the centroidal line of the beam, and k is the curvature of this beam. So epsilon xx is equal to epsilon 0 plus z into k, which represents that when it is the case of combined loading of tensile as well as bending, then there it will be have the strain as addition of both kind of strains, out of which one is the tensile strain due to the application of load taken at the neutral axis, where the distance from neutral axis is 0, and plus the second is due to the bending, and for that purpose this z represents the distance from neutral axis. So as the distance from neutral axis increases, strain starts to increase. When distance from neutral axis is 0, strain is 0, because in case of bending case we know that at its neutral axis strain is always 0 at the top layer, and at the bottom layer it increases a lot for curvature. If it is curved inside, then at inner layer it will have compressive, and its a outer layer it will have tensile load, and that's why this will become equal to z into k. Z represents the distance, k represents curvature, and curvature is reciprocal of radius of curvature. Is it okay? So like this we should understand here the combined uniaxial and bending loading. Is it okay? Then in order to identify, in order to form the strain displacement equations here, suppose this particular strain displacement equations, for that purpose now one more terminology we are going to use here, that is the classical lamination theory. So here itself, for macro mechanical behavior, during last lecture we completed the introductory part, we discussed about the codes, and then we are going further for the Kirchhoff hypothesis and then classical lamination theory. So now we are moving toward the classical lamination theory here. Is it okay? So coming to classical lamination theory, we should have certain hypotheses, we should have certain assumptions. So assumptions are here that each lamina is orthotropic in nature. Is it okay? Orthotropic, we already know the type of materials. During last lecture, we have seen that different types of materials, from anisotropy to isotropy, the journey is isotropic, transversely isotropic, orthotropic, monoclinic, anisotropic. All these are the type of materials, and that's why the here assumption is made that each lamina is orthotropic in nature. Is it okay? So for perpendicular direction, properties are considered to be equal to same here. Then each lamina is homogeneous. Is it okay? Material is homogeneous because all the equations, whatever applicable, in that we are considering that though it is anisotropic, but it is homogeneous. Is it okay? In isotropy also we always assume that material is homogeneous, because if material is heterogeneous, then in case of anisotropic material there will be 36 constants, but material is homogeneous. That's why 21 elastic constants are sufficient in order to analyze the material. For monoclinic 13, for orthotropic 9, for transversely isotropic 5, and for isotropic 5, 2 the elastic constants we are taking for the reference study. And that's why here our first assumption is that each lamina is orthotropic in nature. Then each lamina is homogeneous in nature. Orthotropic, so for 90 degree, what we can say the properties for anisotropy in all directions that are not same. For orthotropic, two direction not same. Monoclinic, one direction is same here. So for is here for orthotropic, it is considered that each lamina is orthotropic, each lamina is homogeneous, line straight and perpendicular to the middle surface, remains straight and perpendicular to the middle surface during deformation. Is it okay? So a line which is straight and perpendicular to the middle surface remains straight and perpendicular to the middle surface during deformation. Is it okay? So this is the assumption decided here. Is it okay? Now moving further with this, let us use this particular, or let us have this look on this particular type of figure here. Is it okay? If we refer this figure, we will come to know that this is x direction, this is particularly y direction, and this is z direction. Is it okay? So x direction, y direction, and this is vertically z direction here. Okay. So the laminate is thin and is loaded by its plane. Displacements are continuous and small throughout the laminate. See, here the laminate is thin and loaded only in its plane. So here this is the plane, and each and every lamina, is it okay? And laminate, number of such a lamina comes in order to form one laminate, that we know. So for this laminate, here for such a number of layers come together to form this M as a moment, and this N, is it okay? The notations which are used here, the laminate is thin. The lamina which generates the laminate, this laminate is considered to be thin and loaded only in planes. Displacements are continuous and are small throughout the laminate. So displacement in this case are continuous and small throughout the laminate, because large displacement means large strain, and large strain means there will be chances of failure. So displacements are considered to be smaller here. Then each lamina is elastic in nature. Each and every lamina, so number of such laminas comes together to form one laminate, and each lamina is elastic in nature. So no slip occurs between lamina interfaces. So here you can see, consider a side view of plane. Now we are starting with the classical laminate theory, and this classical laminate theory, for that purpose, this is the reference figure. Is it okay? Now just refer this particular figure first, which is cross section before loading, and this one is the cross section after loading. Is it okay? Now see, from the middle surface, from this mid plane, if this is x, at the top layer, here it is h by 2. For bottom layer, here it is h by 2. Now here you can say that this direction of x and this direction of z present here. So h is total thickness, if it is considered to be h. Total thickness of this plane is considered to be h. Then half of that is h by 2 and half of that is h by 2. So for top surface, from mid surface to top layer, this h by 2. From mid surface to bottom, again this is h by 2. At any location z, suppose at any location z, because here notation we are using the distance from neutral axis as a z. So that's why at any location z, from this mid surface, suppose this a lamina is present, and from this mid plane, if suppose this particular surface load is applied and cross section is now changed here, is it okay? So this kind of cross section is observed due to the application of bending load. So bending, due to application of bending load, what is happening? This particular cross section, that deformation will exist in that particular surface, and that deformed surface is shown here. Is it okay? Now see, this particular surface and same surface is present here also. Same surface is present here also. Here you can see this particular surface which is present here. So from its midpoint, so midpoint is present here. Similar midpoint is present here again. So this distance is considered to be u suffix 0 here. So u0, that indicates the distance from this particular point to this particular point here. Is it okay? Then here you can consider this particular distance w0 here. Is it okay? At any location here, alpha is considered to be a angle. Is it okay? So now a position which is changed here to the A dash. Is it okay? A is changed here up to the A dash here. Is it okay? So this distance Z, and later on, due to this application of force, whatever the deformation is going to happen here, now this distance, horizontal distance, is considered to be a Z alpha. Is it okay? So this Z alpha, this alpha is the angle, and this Z, that is the distance here. Is it okay? Then horizontal distance is considered to be a Z alpha, and this vertical distance which is given here. Is it okay? Due to the deformation happening, this angle is alpha here. Is it okay? Like this is shown here. Then this U is equal to u0 minus z alpha, that you can see here. This u is equal to u0 minus z alpha here. So u0 you can see here, that distance from point which is shown here to this corresponding point here. So this particular perpendicular distance which is u0 shown here. Is it okay? You can see here this distance, this perpendicular distance is u0 here. So u0, which is perpendicular distance, minus z alpha, because this particular distance, so previously point A is here, after deformation this point is changed here to the A dash, then positional difference between A and A dash will be u0 minus this z alpha. Is it okay? So this particular point is shown here it as z alpha. So u0 minus z alpha, that is the positional difference between A and A dash here. Is it okay? That you can see here. So u is equal to u0 minus z alpha, that is shown here. The displacement u in x direction is u is equal to u0 minus z, and this particular alpha, which is considered to be an angle here, so that angle is differentiation of w0 to the x. Is it okay? So here this is one kind of, we can say, as one parameter, because number of degrees of freedom whatever considered here, this particular degrees of freedom, out of which u is the displacement along x-axis, v is the displacement along y-axis, and w is the displacement along z-axis. Is it okay? So this particular z-axis displacement, and which is here from this w0, if you take its differentiation, then that becomes equal to this angle alpha here. Is it okay? So with the equation u is equal to u0 minus z alpha, because positional difference of A is taken here. Initially A is positioned at this point. After deformation, the position of A dash is here. So the distance difference between A and A dash, that is u0 minus z alpha here. So u0 minus z alpha here. So this alpha is substituted here, and zu is equal to u0 minus z into dou w0 upon dou x here. Is it okay? So taking a cross section in yz plane gives the displacement y direction here. Similarly, same is applicable for v also. If u is the displacement or deformation along x axis, and if v is the deformation along y axis, then here the strain along x axis is dou u by dou x, that already we know in analysis of mechanical element, in case of solid mechanics, we have studied this particular part. So epsilon x is equal to dou u by dou x here. So substituting the same thing here, here 0 represents at its neutral axis only. Is it okay? And then by substituting this particular value here, and by taking the differentiation of this, we get that dou u0 upon dou x minus z into dou 2 w0 upon dou x2. Is it okay? So in terms of this u, that is represented to be a, if we take the differentiation of this particular equation, dou u by dou x, that is nothing but epsilon x. Here it is dou u0 upon dou x and minus z into dou 2 w0 upon dou x2. Is it okay? So which is the differentiation of this strain has been taken here, and after taking the differentiation we got here dou u0 upon dou x is equal to minus, so this particular z into dou 2 w0 upon dou x2. Same thing is here for strain along y-axis and this shear strain dou u by dou y plus dou v by dou x here. Is it okay? So substituting that particular equations here, dou u by dou y, where u is nothing but here it is taken at its a central location, midterm locations here, and by substituting all these terms here, what we get, we write epsilon x, epsilon y, and gamma xy as here as usual along x-axis but at neutral axis, along y-axis but at neutral axis, and along shear direction but at neutral axis. Is it okay? So this is epsilon x at its neutral axis, epsilon y at its neutral axis. This is epsilon gamma xy at its neutral axis plus this z we can consider as the distance from neutral axis. Is it okay? And these terminologies that are nothing but the curvatures here. Is it okay? That are the representation of the curvature is here, because zk already this k was the curvature was used. Here we are representing with the help of alpha here in order to understand this equation, and this is again in the form of epsilon is equal to this equation u plus epsilon x plus z k in that form. Is it okay? Like this, this particular equation is represented in terms of strains along x-axis, along y-axis, and along shear axis. Is it okay? So this is at the central location, which is here, and this is again curvature, curvature at x, curvature at y, and curvature at xy. Like this has been used here. Is it okay? So therefore the laminate strains can be classified, can be written as epsilon x, epsilon y, gamma xy. So this is at its central location, and this we consider as a curvature at x, curvature at y, and curvature at xy here. Is it okay? So like this, here we will get the value of curvatures, and this is nothing but the classical laminate theory which is used for the analysis of this stresses and strains in case of laminates. Is it okay? Then again, the stress sigma x, sigma y, and tau xy. Already the stress strain equation for the composite material we have this correlation we have established in previous chapter, and while establishing that relationship between stress and strain, the terminology of Q11 bar, Q12 bar, Q16 bar, that is already used. By considering this angle theta, different angle thetas, and the strain values, here we can have this. But if we want to identify the stresses sigma x, sigma y, and tau xy here, then let us multiply with this particular matrix of Q11, Q12, Q16 to the strain values and for the curvature values here. Is it okay? So like this, we can identify the stresses as well as strains here in case of composite laminate for each and every lamina here. Is it okay? Like this, here we can understand here this k minus 1, k plus 1, like this. Is it okay? So this is the distance moving from the mid plane. These are different lamina in the total laminates. Each and every lamina has a distance h0, h1, h2, h3, like this. Total h is considered to be h, and out of which half is h by 2 and another h by 2 here. Is it okay? Like this, force and moment resultants related to mid plane strains and curvatures that are shown here. So h0 is equal to minus h by 2 from the top surface, h1 is equal to minus h by 2 t1 at the plus t1 at the bottom surface. Is it okay? So from top surface, bottom surface, like this nx, ny, and nxy, so that is supposed to be identified. So the resultant forces per unit length in case of XY plane, so that is given here. Similarly, in case of this lamina, the moments per unit length, that is also given here. Is it okay? So this Nx, Ny and Nz, so that is identified by integrating the global stresses in each lamina and the resultant forces per unit length along x-axis, along y-axis and along as a shear force that are identified here. Similarly, this moments along x-axis, moment along y-axis and this shear moments that are also identified by taking the integration of this particular stresses along x, y and this tau xy. Is it okay? So here we can identify totally the resultant forces and moments in case of the composite material whenever these are in the laminate form or lamina form. Nx, Ny, Nxy, Mx, My and Mxy that are identified by taking integration minus h by 2 to h by 2 minus h by 2 to h by 2 sigma x sigma y tau xy dz and sigma x sigma y tau xy into z into dz. So these are the resultant forces and these are the resultant moments here. Is it okay? So that we should understand here in order to get the identification of this the resultant forces and resultant moments in case of laminates. This is very important part in case of the composite laminates here. Is it okay? So with this we have finished this part of lamination here. Is it okay? Any doubt here?
No, sir.
Any
No.
doubt?